Hello and welcome today to basically an introduction to electricity. Here, basic things we're going to be talking about are the basics of electrical circuits, since usually those are generally how we represent electricity at the very start. So basically, what is an electrical circuit? Well, typically it would be a system in which a metal wire or something is put, and we all know that metals can conduct electricity because of the free electrons. So what we do is we give energy to these electrons, force them to travel in a current, so that later on they can give their energy to other appliances such as light bulbs or motors or some buzzers. And basically that is the basis behind nearly everything in our technology today, these electrical circuits, which is why they are so important. So to start us off, what really is electricity? And there are many definitions, but one of the most simplest ones is energy caused by the movement of charged particles. So here, see some moving electrons. Let me show that again. Basically, these electrons have energy, which is why they're moving. And that energy is probably caused by something to do with their charge. And basically electricity is the energy of the movement of those charged particles. And keep in mind that electricity is not just by electrons, but anything charged, basically. You can have a flow of ions in an electrolyte, for example. Okay, so let's look at one of the most basic circuits you'll ever lay your eyes upon. Here, we've got a battery, which is providing the energy for the electricity. Well, energy for the electrons, sorry. And here we've got the light bulb, which is the thing taking the energy from the electrons. The energy is then converted into light and heat energy, which is of course how light bulbs work. How it is transferred into that is due to the internal workings of the light bulb, which we will not discuss in this chapter for overcomplication reasons. So anyway, let's look at some circuit concepts. Basically, these are the underlying principles in which we'll need to work upon when discussing electricity. The first of which is charge. Now we all know that electrons have charge, and just happens that we have a good way of measuring these electrons in suitable appropriate numbers. Basically charge is measured in coulombs. And a coulomb is exactly 6.24 times 10 to the power of 18 electrons. Now, why do we have this charge coulomb thing? Well, when discussing electrons, each of these electrons is so small and the energy is so insignificant that we need to measure each unit in large numbers of electrons. So charge is basically a measure of how many electrons there are. The more coulombs, the more electrons there are that are flowing. Next we've got current, which is measured in amperes. And it is basically, very simply put, a unit of electron speed. So basically, more amps, or amperes, the faster the electrons are flowing. Keep in mind the symbols next to these. Charge, when you're discussing it in a equation, would be represented by Q. Coulomb is represented by C. Current, when discussed in an equation, is represented by I, the ampere represented by A. So next we've got voltage, measured in volts, both with a symbol of V. And it is basically a unit of electron energy, so how much energy these electrons have would be measured in volts. So the more volts, the more energy the electrons have, the more energy the electrons receive from the battery or distribute to the other components, such as the light bulb. Next we've got resistance, R, which is measured in ohms, and the symbol for that is the omega sign. Now what is resistance? Basically, resistance is the hindrance of electron flow. So basically, the more resistance, the less current you'll have. Resistance is trying to stop the electrons from flowing. And so the more resistance, the less effectively the electrons will pass through the circuit. Think of it like when you're playing American football. You're trying to get to the other side with the ball, you're the electron, but the resistance are all those big buff guys that stand in your way trying to knock you down. So basically, the more resistance, the harder it is for electrons to flow. The next is energy, which is measured in joules. Now, for this specific reason that energy is so general, I did not put a definition for that, which would contribute only to this topic of electricity. But I'm assuming every person there has a general idea of what energy is. Second, we've got time, which is measured in seconds, and I am very sure all of you know what time is. So alright, let's get on to some electrical equations, which govern everything that happened in the circuit. The first of which is voltage equals current times resistance. And I put two equations to the side. I think one that'll be easier to discuss is current equals voltage divided by resistance. Now, we said that current was a measure of how fast the electrons were going, and a voltage is a measure of how much energy they have. So if they had more energy, they would be going faster. But then we also said that resistance is trying to stop the electrons, so the more resistance you have, the slower they would go. So we end up with current equals voltage divided by the resistance. And that equation really does make sense when we take into account the definitions. The second equation is current equals charge over time. We said that current was a measure of how fast they went. Charge is a measure of how many electrons. And there's time measured in seconds. So basically, how fast they're going is how much of it passes a single point in the circuit over a certain amount of time. Let's take an example. If my current was 5, that would be 5 coulombs passing a single point in 1 second, let's say. Easier definition, let's take trucks. If each coulomb was a truck, if my current was 5, I would have 5 trucks passing a single point, let's say past the dustbin, in 1 second. If my current was 2, only 2 trucks would be able to pass the dustbin in the space of 1 second. So next we get to voltage equals energy over charge. Now we said that voltage was a measure of how much energy each coulomb has, so it only makes sense that voltage is the amount of energy per charge. So those are your basic electrical equations. Another basic equation would be the power equation, but we'll discuss that in the power chapter. Alright, next are your circuit symbols. Now basically these symbols are just the appliances or devices that are used in the circuit. If you look carefully, maybe maximize the video screen, you could see that we have a battery cell, a light bulb, a resistor, which basically just gives resistance, or, well, everything gives resistance, but with a resistor you know exactly how much resistance it gives, which is very useful. A variable resistor, which is exactly like a resistor, except you can actually change the resistance at will, which is useful. A motor, which is kind of like basically something that moves in response to the electrical energy, such as a wheel, or something like that. A voltmeter. Now a voltmeter, if you put it inside the circuit, it measures the voltage over a certain appliance or object. For example, if you measure the voltage over the battery, you can get a clear measure of how many volts the battery is giving to the coulombs. If you measure the voltmeter over the light bulb, you get a measure of how much energy or how much voltage the light bulb is taking from the electrons or coulombs. Then you've got your ammeter. You can place this anywhere on the circuit, and if you place it anywhere on the circuit, it just basically tells you how much current is passing through that point in the circuit. Now the next one are the switches. You've got an open switch and a closed switch, and the concept between switches is very simple. If you have a closed switch, then current can pass through it. The electrons, the coulombs, can pass through it. When you've got an open switch, there's no current, simply because it is disconnected. And circuits always need to be connected to work. Alright, so now we've got the concept of energy transfer, which is basically the battery is giving energy to the electron, and the electron is passing the energy over to the light bulb. If the light bulb is not to break, or if the light bulb is to even work at all normally, then the energy given to the electrons must be the same as the energy taken from the electrons. I'm not sure if it's really visible in the animation I've made, but this electron is actually jiggling and vibrating more as it goes to the light bulb. But then after it passes, it loses all of that and just goes in really uniform motion. That is just basically to show you about this concept of energy transfer. Keep note that in a circuit, electrons flow in a certain direction away from the small side. Why? Well, we know that like sides repel and opposite sides attract. Now if you've got a battery cell such as this, the big line is always going to be the positive side. So the electrons will be attracted to that side, and since the small line is the negative side, the electrons will be repelled from that side. So yeah, basically at that point it gives all its energy to the light bulb, and after which the electrons are left with 0 voltage to return to the battery and get their fresh supply of voltage or energy to be given to the light bulb. And a few more key terms that are worth remembering are electromotive force and potential difference. Now, what is electromotive force? Basically, it's the energy given to the coulombs by the battery cell. And potential difference is the energy taken from the coulombs by the light bulb. So basically, you've got a potential difference across the light bulb of how much energy it takes, and electromotive force on the battery of how much energy it gives. Both of these measured in voltage. So basically, that's energy transfer. Now, the last thing we'll be discussing in the introductory lesson, series and parallel circuits. Okay, so we've already seen a series circuit. It's very simple. The electrons all follow the exact same path. We see that they can only go one way, they can only hit the same light bulb, and they can only come back in the same journey home to the battery. They have no choice. It is just there in the circuit. Whereas in a parallel circuit, we see here that they actually have two paths. If you look here, the electrons have a 50-50 chance of either going to the first route or the second route. So basically, if you've got a current flowing through from the battery, half the current will go to the first light bulb and half the current will go to the second light bulb. However, if the two light bulbs are identical, the potential differences of the light bulb, basically how much energy each light bulb is getting, will be exactly the same. However, the current flowing out of the battery is exactly twice as much as the amount of current these light bulbs are getting, simply because the light bulbs are only receiving half of the current. And that is a parallel circuit. Basically, when the electrons have more than one option, when they have more than one choice of where they want to go. So, that ends the introductory lesson, and I hope you gained something really good from this lesson. I hope it improved your understanding of the foundations of electricity and electrical circuits, and I will be giving more lessons on concepts such as power, resistance, and current. So keep checking. And that's it for the day. I'll see you next time.